Today's topic is artificial intelligence. Without AI, most of our favorite games wouldn't exist in their current form. But what happens if AI plays the games that we design, or even designs the games that we play? On behalf of our new overlords, I welcome Julian Togelius from New York University.
Thank you, Anna-Kaisa, for the introduction. So I'm Julian. I'm here from New York. Just flew in yesterday. I'm surprisingly awake. I hope to stay awake throughout all of this talk. I hope you will too. Tell me if you fall asleep. So I'm representing New York University and also our startup Model.ai, trying to commercialize a few of these ideas. Let me start with who I am, because it's good for you to know who this person is talking and what you're dealing with here, and also because I like talking about myself. So basically, I finished high school, surprisingly, despite being very bad at mathematics and hating it, and promising myself that I would never, ever in my life have to have anything to do with maths again. Right. So I wanted to understand the mind. So I started studying philosophy and psychology because I wanted to understand the mind, and that was how you would do it. This was back in my native Sweden, at Lund. And while I did this, I realized that sort of progress happens really, really slowly in philosophy. Like once every 50 years or so, someone comes around with a truly good idea. And that might not be me, so I didn't have the patience for that. Psychology also is like really boring because the methods are very blunt. You can't really get much deep knowledge out of it. I felt that basically, if I wanted to understand the mind, I needed to build one. So I needed to move into artificial intelligence. So I took computer science classes. Then I went to University of Sussex in the UK to study biologically inspired artificial intelligence, basically copying simple animals and copying evolution to create neural networks that control simple animals. And then I moved to the University of Essex in the UK again to do a PhD on what I thought would be evolutionary robotics. So using artificial evolution to create neural networks that will control robots. I thought that was really, really cool. But then I figured out that actually robots are really slow and they break down all the time, and you have to change the tires, you have to pour new oil into them and replace the batteries and all kinds of stuff, and I didn't want to deal with any of that because I am not very practical and like physical things are boring. So somewhere during my PhD I thought that, well, you could use games, particularly video games, for testing and developing your AI in the same way. So I started doing that, and that was around the right time when interest in using video games as AI testbeds were just about sort of getting started. And so I was basically doing games for AI. And then it struck me that you could do it the other way around as well. Not only using games as a testbed to test your algorithms, but also using these algorithms to try to make the games better. So doing AI for games as well as games for AI. And that's what I'm doing. I've been through a couple of different places. I worked with Jürgen Schmidhuber in Switzerland for a while. I was working in Copenhagen, and now I'm at New York University, trying to advance AI through games and trying to advance games through AI. Let's start with AI, artificial intelligence. What is it? Well, those of you who have seen 2001, A Space Odyssey, probably the world's best movie. Feel free to disagree, but if you do, we have to take that outside, okay? You might think that basically this is not what AI is. This is a murderous computer that kills the ship's crew in order to save the mission. Sorry, I just ruined the movie for you if you haven't seen it. This is really not the picture of AI that I want to give, really. Let's start from the beginning. What is artificial intelligence? Okay, let's be extremely boring about it. It is basically making computers able to do things which currently only humans can do. It's a very, very boring definition, and that's why I like it. Now let's talk about games. What do humans do with games? Oh, play them? Yes, thank you. This is always the first answer I get. Play them. It comes automatically. Games. Yes, you play them. What more do humans do with games? Yes?
Learn.
Learn? Learn what?
Learn to play them, or you can learn about the world in general.
Right. And you can learn to play games, learn about the world, and not learning how to shoot people, right?
Well,
No, of course not. Yeah?
To watch games?
Watch games, yeah, people watch them. Yes?
Make games.
Make games, definitely.
You optimize.
What do you optimize?
Your score.
Your score, right. You play them well as to optimize the score, that's right. A couple of things. We're going to get to several of these and maybe some other things that you did not think of in this talk. But let's start, because everybody always thinks about playing games. Let's start with that. Humans play games. Why do we play games? Well, we play games because it's fun. Why is it fun? For a number of different reasons. We're still trying to figure this out, etc. But one of the important reasons why it's so engaging is that they are designed to challenge our minds. A good game challenges one or several different cognitive capacities, and they're also designed to be sort of learning experiences where you start out with a simple version of a task, which you can do, and then it gradually gets more difficult, introduces more complexities, and you get better at it. So games are extremely pedagogical. A well-designed game is essentially a well-designed teaching tool. This is pretty cool. This is also why they're extremely relevant as AI benchmarks. You can use this same sort of quality of games that are designed to teach humans how to play them, to teach machines how to play them. And because well-designed games are those that are engaging for us, are designed to challenge our minds, then that also means that they're extremely relevant as AI benchmarks. And of course, I'm not the first one to think about this. Basically the history of games and AI is as old as the history of AI. Alan Turing himself, invented or reinvented, depending on how you see it, the minimax algorithm for playing board games, and used that to play chess against one of his friends. Before even having a functioning electronic computer, he actually executed the algorithm on paper and sort of used it to play. And this here is not Alan Turing, this is John McCarthy, one of the originators of, or the early artificial intelligence pioneers, playing chess against a computer the size of a room, back during the day when everything was in black and white and computers were the size of a room. Chess was one of the really important early AI problems, and for the first few decades of AI, lots of people worked on chess. It was considered really important because why? Because chess is sort of the essence of intelligence. You're sort of trying to plan, make long-term plans, and you're trying to sort of outsmart an opponent. You need to sort of basically predict what your opponent's going to do and come up with long-term plans that might actually work and not be led into any traps that the opponent sets for you. Sort of, people had this sense that if you come up with a computer that could really play chess well, you'd have sort of solved it. And this made sense at the time. And now, fast forward to 1997, the world was in color, and well, this particular computer was the size of a room. This is IBM's Deep Blue winning over Garry Kasparov, and Garry Kasparov was the world's reigning chess champion at the time. There was a big publicity stunt for IBM when they could actually have a computer winning over the best chess player in the world. So what does this mean? Because for a long time you've been saying that basically chess was sort of the epitome of intelligence, and now we had a computer that could play chess better than the best human. Had we solved intelligence? Had we achieved artificial intelligence? Well, I mean, Deep Blue, when you sort of open up the hood, essentially look at what the code actually does, it's just a search algorithm. It's a search algorithm with a lot of bells and whistles. It's really, really complex, but it's just a search algorithm. Also, perhaps more importantly, Deep Blue cannot tie its shoelaces, it cannot write a love letter, it cannot make soup, it cannot even play checkers unless you recode it a bit. So how intelligent is it really? People were thinking that chess maybe isn't the best sort of, benchmark for intelligence. Maybe we should look at another board game. So people started working in Go. And then 2016, this happens. This is DeepMind's, so it was then Google DeepMind's AlphaGo software winning against one of the world's best Go players. And with that, sort of board games is sort of done. So this was the hardest for computers board game that basically had been attempted. So what we had is we have basically computer supremacy in all important board games. Luckily, this is not all we can do. So AI for playing board games is a very, very tiny part of all of AI applied to games. As we talked about, you can do a lot more than playing games, and you can also, there are also many more interesting games than board games. For example, video games. So I'm showing here examples of StarCraft, as you probably are aware of StarCraft, and a version of Super Mario Bros, and a 3D racing game called Torx. I'm showing these because in the AI and games communities, there's been long-running competitions based on each of these games, and the StarCraft competition is still ongoing and actually getting more and more relevant and more important, though there's less work currently on Super Mario Bros. And on car racing. So let's see what we have here. The Mario AI Championship was a competition we started back in 2009. Back when, so it happened that I discovered that Marcus Persson, also known as Notch, he later on went and this game called Minecraft. But back then, before I'd done Minecraft, he was actually sort of an approachable person, and he answered emails, which I think is surprising when anyone answers emails. I mean, I don't. But he had made a sort of open source Java clone of Super Mario Bros. And me and a student hacked this into an AI benchmark. So you can connect your own sort of AI agents to it and play it, and then we made a competition out of it. It had a level generator, so every time you played it, you got a new level. And we sort of ran this at a couple of conferences, asked people to submit their best Mario playing agents, and we thought that this would be really interesting to see. The problem was, and this made us really, really sad, for the first ever Mario AI competition, this agent was submitted. And what you can see here is that this agent is just too good. It seems optimal. You look at this, and you could definitely not play Mario this way. I mean, you couldn't. It's like pixel precision. Every jump is exactly timed where it should be, and it sort of has a spooky quality. I love showing this video because everybody gets absolutely transfixed. There's a couple of moments which basically, which everybody reacts to because it's sort of, you naturally imagine yourself in the position of this agent, and then you're sort of shocked at like things they can do, like this. You can't do that. And really, really, I mean, the really sad thing about this is that this was based on this extremely simple algorithm that people learn in like first or second year computer science class. Any idea? Anyone? Nope. So it's not the fancy neural network. So it's the Astar algorithm. It's a classic planning algorithm that is used for path planning all the time and is used in like almost all games all the time. So basically what happens is that it plans in state space. It uses a simulation of the game, and then it looks at every point in time, it just tries to get the right to the right end of the screen. So it sort of basically looks at what actions it has, lays them out. Okay, these are the different actions it can take. Looks at the one that seems to be getting closer to the right end of the screen and sees if we can get there, like, oh no, that's not so good. That action would lower my value very much because I would die. So let's not take that action. Let's look at what's the next best action I can take and then do that. And then you expand the actions from that. So basically, and then you add them to the list of all possible actions. I'm obviously simplifying here. It is a little bit more complex than that. But the important part is that it basically just uses a simulation of the game, and then it searches in that simulation. So it uses what's called a forward model. So we were really saddened because we had thought we had a good AI benchmark, and then it seems that someone could almost basically play it optimally that way. So we thought about how could we possibly make this benchmark better? How could we save this? So we changed the level generator, so it started creating levels that had these sort of dead ends, where it would have to sort of basically run back to a place it had been before. And this is sped up a bit. What you see here is this Astar agent trying to play this game. And to get out of here, it's actually not that hard. You basically just need to walk back a bit and jump up on the top of this overhanging ledge here. But the agent can't find that because it's just searching and searching and searching around and trying to get to as far right as it can. But yeah, it's basically greedy. It's a short-term optimizer. And it would need to figure out that this is not working. I need to move all the way back and find another path. It can't. So this was interesting. This is an illustration of how it looks. This is one of these overhangs that traps this algorithm pretty well. And for the next year's Mario AI competition, we had this thing submitted, which is a combination of using Astar algorithm at the very bottom, something called evolutionary computation, which we'll get to in a bit at the top, and a set of rules which are evolved using this evolutionary computation. It's a mess. It's basically a bunch of different things that don't seem to fit together, but it is so far the best Mario playing agent that I know of. And it's pretty good, right? Of course, playing a game well is not necessarily everything you want always. We also ran a version of this competition, which was sort of a Turing test, which is basically where we asked people to submit the best agents, and then we asked spectators to look at these agents and see which one, both videos of agents and videos of humans, and try to tell humans from agents, and try to find the most human-like playing agents. And here we had a number of different results. So this, for example, is my postdoc, my former postdoc, training a Bayesian network, so a machine learning method, on her 5-year-old niece playing Super Mario Bros. And it starts looking pretty human-like. But we also figured out that you could easily take an existing method and fix it up some way. You could basically make it wait a bit for, now and then, sort of stop and wait a bit, which humans do a lot when they need to think. You could make it seem to take actions and fail, which is also very efficient. This is something that people rank as being very, very human-like, and so on. And also trying to sort of not jump off at the very last pixel. So anyway, I'm not the only one doing this. In recent years, there's been sort of an explosion of interest in people using video games to benchmark the AI algorithms. So there's this car racing competition I talked about, the Mario AI competition. There's a very common StarCraft competition. It's very popular. There's a general game playing and general video game playing competition. There's also the Atari. There's a set of games based on the old Atari 2600 game console from the 70s, which is a very, very primitive thing, but these are very popular to try things on. One thing that has been used very much And if you look in the literature, there's a lot of work on trying to use deep neural networks, as they're called, and a technique called Q-learning with this. It's almost so that basically you think that this is the only thing that people are using. At least if you're Jesus Quintana, then you think that this is, I'm not sure if anyone gets the movie reference, but from The Big Lebowski. It's like definitely the best algorithm for game playing. Well, no, actually, it really depends on the circumstances, and it really depends on what you have. It turns out that you have a lot of different methods that can be used for playing games. And which one to use depends to an extremely large amount, on what the characteristics of the game are, and whether you have access to the internal state of the game, whether you have access to a simulation of the game, so you can sort of do some sort of planning or not. In any case, there's a lot of work going on learning to play games, or AI for playing games. But we have a big problem with almost all of this work, and that's the overfitting that goes on. So people come up with AI methods for playing StarCraft, or for playing Super Mario Bros., or for driving cars on a racing track, and in almost all cases, these methods don't work in any other game. So the best Dark playing AI cannot play Super Mario Bros., and the best Super Mario Bros. Playing AI cannot drive racing cars, or play StarCraft for that matter. Not only are they bad at it, the inputs and outputs don't match. You sort of can't do it. It doesn't work. If you're interested just in coming up with AI to play particular games, this is not a problem. But if you're interested in actual general intelligence, so learning how to make AI better in general, this is a problem. Because real intelligence is about doing multiple things. So I'm now going to show you something slightly inappropriate. This is the sort of thing I tell people to never have on their slides. And I'm sorry if this is not what you want to see. I'm going to show you an equation. I really do believe you should never put equations on slides, but this is a very good equation. This is Shane Legg and Marcus Hutter. Shane Legg was my colleague back at IDSIA in Switzerland. He later on went on to found DeepMind. And they were just thinking about what is intelligence. And they came up with this this sort of formula for what they call universal intelligence. The universal intelligence of a policy, pi, you can think of that as an agent, is the reward it gets, so how good it is, over all possible environments, inversely weighted by the complexity of the environment. So that basically, how good are you? How intelligent are you? Well, that is how good you are at all possible tasks, but let's count the ones that are easy to describe more. So it's more important how good you are at sort of more fundamental tasks than those that are very, very specific. I think the intuition behind this is very, very sound. I think it captures something very important about what intelligence is. However, it is not clear that you can actually measure this, or you can't measure this, because you have to measure it over all possible environments in the world, and that's impossible. And then you have the Kolmogorov complexity of these environments, which is incomputable. So it's you can't measure this. But we can try to approximate it. And one sort of route that me and taken is try to come up with an AI that can play more than one game. So basically, can you come up with a way so that you an interface where you give where you plug different AIs in, and they play multiple different games, and you test their intelligence that way. And that was the thought behind what we called the general video game playing competition. So we developed a simple sort of game engine that lets you submit controllers, currently in Java. And the game engine lets these controllers play a number of unseen games and scores them. So basically, you don't know what games you're going to play when you write these controllers. You submit it to competition, and then it plays 10 new games that is never seen before, and you get a score back. And then sort of we add these games. Now these games are used up. They're sort of so we add them to the training set of games you can train on. We came up with a specific description language you can code these games in, and so on. So what does it look like? Here's a human playing a version of, it's inspired by the overworld of Legend of Zelda. You fight monsters, you take keys, you get to the door, you exit the level. It's fairly sort of standard sort of 8-bit to 16-bit two-dimensional game design. Let's see how well a random player plays this. The random player just takes random actions. It dies. Turns out taking random actions is not very good. So what actually does work well? So let's look at this algorithm called Monte Carlo tree search. It's been very, very popular for the last 10 years since it basically was used to, it was invented in the context of playing Go. It's a stochastic tree search algorithm, and it's extremely versatile. Let's see how it does. You basically have it running around, taking pretty good decisions, not looking far ahead in the future, finding the key, and then like, okay, where am I going? I have to plan really far ahead to get to the door. Okay, the door, there we go. It's pretty good. And then you can use the same algorithm for playing, for example, Space Invaders. This is Space Invaders being played by a human. Not going to show you all of this video because it's not a terribly exciting game. But yeah, you get the point. You need to kill the aliens before they kill you. Space aliens, nothing else. Here's the same game played by a random player. Random player still takes random actions. And it still turns out that random actions isn't that good. Gets you killed. And here's the Monte Carlo tree search algorithm playing the same game. And being very good at it, actually. It might not look like it's doing anything useful at the moment, because it's busy getting rid of these fortifications. But then it falls into a pattern where it actually is very good at killing these aliens. Right. And playing this game is not very advanced. That's sort of simple. The interesting thing here is that the same algorithm plays both games, and it has no idea what it's going to play until you suddenly sort of basically give the algorithm the game, and then it has to play it. Here's the game Balderdash. Any of you played Balderdash? Okay, quite a few of you. It's a fantastic classic 80s game, which has both sort of action elements and strategy elements. You need to dig out the dirt, and you need to push boulders and sort of make them fall on each other in such a way that you get to these diamonds. When you get 10 diamonds, you can exit the level. And you need to not get stuck. You need to not get caught by these monsters. And it's actually pretty tricky. You need both reactions and planning. The version of Balderdash in this framework is somewhat faithful to the original and actually playable. It's my PhD student trying to do this here and clearly playing a bit slower than I would want him to. Let's see a random agent do this. The random agent is not very good, still. Oops. And let's see our sort of wunderkind Monte Carlo tree search algorithm try the same thing. And what you can see here is that this game is hard. You really need to plan far ahead, and it also doesn't handle some of these random movements from these enemies very well, so it failed. It turns out there are no algorithms we know of that can consistently beat all levels of this Balderdash game, and it's pretty fascinating because of the combination of stochasticity, long-term planning, and the sort of fast reactions you need. So our idea here is that you can actually sort of use this as a test bed to sort of develop more and more general intelligence. So you can basically gradually learn, you can start on simple levels and train these agents to get better, and then you can go on to harder levels, and in the same way you can sort of go on to play harder games and so on. And then you can use that to sort of learn how to learn as well. You could question this idea. Is this actually the right thing to do? If you want to learn general intelligence, should you really be playing games? Is that, you know, do you get all the kinds of intelligence you need from playing games? I mean, empathy, body awareness, linguistic interactions. You might say that this is not everything there is. But then again, I mean, there are so many different types of games to play. There are these role-playing games that feature a lot of like textual interaction. They feature a lot of sort of long-term planning, emotional reasoning, and so on. There are procedural generated text adventure games, and so on. There's really sort of such a diversity of games out there these days that I think it's fair to say that if you have a unified interface where you can have an AI algorithm that can learn by playing more and more games, sort of more general skills, then you could actually train it to have something like general intelligence. And if we get to the point where we have an agent that could play any game within reasonable limits, it needs to be a good game, say any game from the top 100 of the App Store or of Steam or like something like that, Nintendo Switch Store, and you basically give it to it and it will play it after like maybe training for like a couple of minutes or an hour or something, then I think we'd reach something like general intelligence. If general intelligence exists. I'm not sure it does, but if it does, I think that's what we have. But let's move on. We talked about AI for playing games, almost exclusively now. Let's look at the other things you can do with games. Let's look at the sort of AI for games side as well. So we play them, sure. We study them. I have these colleagues that are game studies people, like Anna-Kaisa here, basically studying, well, in her case, like how game developers, what they do, but also in many cases they study games as you would study literature or movies or something like this. And then people explain games and teach games. People do that a lot, basically. So you want to show your best friend or your mother or something like this, or your kid or something, how amazing Bloodborne is. You probably need to explain it to them and sort of teach it to them. People build content for them. So there are so many games like Minecraft, obviously, but many other games like Little Big Planet, Super Mario Bros. For the Super Mario Maker, and so on, where people put lots of content online for the game, and people develop them. So let's look at the design and develop thing. And I want to take you back to the 80s, which is always a nice thing to do, at least with audiences of a certain age. This is Elite. It's a game that was released in the early 80s. You fly around in space, and you can have space battles with various other spaceships. There's a sort of very simple 3D representation, and you can fly between stars and the space stations, dock at space stations, and so on. There are lots of different star systems, and I mean lots of different star systems. I think one of the versions had 4,096 different stars. Each star had like planets and space stations around it, and lots of different spaceships flying around in that region of space. And it was really complex. And you dock at a space station, and at a space station there are different kinds of cargo, and the cargo has different prices. You can make your living by trading this cargo between different space stations. And there are missions as well, where you need to find lost spaceships and stuff like this. And this thing fits in memory on a Commodore 64. Now, for those of you who were not there at the time, the Commodore 64 had 64 kilobytes of memory, so 64,000 characters. How could you possibly fit 4,000 planets or 4,000 star systems in 64,000 bytes of memory. It is like literally impossible, right? The thing they did was that they used the code of the game as seeds for a random number generator that was used to construct the star systems in runtime, including the names of everything, of like planets and star systems and ships you were going on a mission for, and the locations of everything and what kind of spaceships there were there and so on. The rumor is that they actually printed out all possible names that the name generator could generate to make sure there was no obscenity in there, which is surprising to me because who cares about some obscenity? They were clearly not Nordics. Anyway, so it was really, really fascinating because you were sort of overcoming this simple or this limitation of the computers of the day by generating things during gameplay as it happened. And you may think that this is a cute historic anecdote, but today's computers are so much more powerful that we don't need this anymore. Because look, you can get a computer nowadays which literally has 1 million times the memory that a Commodore 64 had. So, you know, why would we care? However, that would be committing the Bill Gates fallacy. The Bill Gates fallacy, 640K should be enough for everyone. So actually, nowadays you have things like No Man's Sky. No Man's Sky is essentially the direct spiritual descendant of Elite. It looks a lot prettier, but it's very similar in the sense that you fly around in a universe with more stars than you could possibly ever visit in a lifetime, and they're all generated as you go there. But the seeds that are used to generate them are stored away. So if you come back, you're going to see sort of the same star system being generated and look the same again. This is one very, very important use of procedural content generation, to generate things online as you play it, to make big worlds possible. Another thing is this. So back in 1980, Glenn Wickman and Michael Toy at the University of California, Santa Cruz wanted to play Dungeons & Dragons on their computer. However, they didn't want to write their own Dungeons & Dragons adventures because they wanted to play them. So they, and if they already knew everything that was going to happen, it would be no fun to play it. Also, they didn't have enough space on the hard drive to store them. So what did they do? They make this simple game called Rogue. It's actually not simple, it's complex, but it looks simple. It's a beautiful ASCII graphics here. They make this game called Rogue, where you run around in a dungeon and you you explore it, you walk through rooms, you find treasures, you fight monsters, all these things. And every time you play it, there's a new dungeon generated. And they did this both to sort of save themselves development time and to save hard drive space and everything like this. And this was an very important part of game history, because there's a whole genre of roguelike games that are inspired by this, and basically the same idea that every time you play it, you get a new world to play with. Diablo III, for example, so take a high-profile example of a very successful game, is essentially the same game. It looks prettier and it's more real-time, but the core idea is that every time you play it and every time you go to a new level, you have a new sort of geometry of this level and new items to discover. Dwarf Fortress, anyone played that? Yeah, I'm impressed. I can't play it. I had a PhD student that actually played it for fun. Every time you start a new game with Dwarf Fortress, it creates a new world and it simulates the geological development of the world, the political development, the history of the kings and queens and even the gods and so on, to give you a new sort of pantheon and a new sort of history and a new geography every time you play it. And then you can control the game down to the level where you can put different socks on each foot of an individual dwarf inside this giant fortress that's under your control. It is essentially unplayable, but I love it as a sort of conceptual art. It follows in the same tradition. But other games you might not think of, like the whole Civilization series of games, where you control an empire from Stone Age to modern ages, it really rests on the idea that every time you play it, you have a new world to explore. Otherwise, it wouldn't be the same game at all. It would be a much less interesting game otherwise. Spelunky, I don't know if you play that, one of the best sort of action-focused games to come out in the last half decade or so. It's essentially a cross between Super Mario Bros. And Indiana Jones. You explore these caverns and whip snakes and stuff, but also importantly, every time you play it, you have a completely new set of levels, so you can't get away with just learning the levels, you actually have to get good at the actual game. All of these games sort of rely, these are just like some token examples, rely on the idea that you can generate a game, or some aspects of the game as you go along, but also much more sort of, mainstream games, like almost any game, this is just a token example, that features large areas of vegetation that is supposed to look lifelike, generates some of it as you go along, because you don't want to use human resources on modeling every single tree, because it takes too much time, and you can't store all of that in disk, and you don't want to use all the disk space to store all that. You want to sort of generate, it's like a practical necessity to generate some of it. It's another example. The Boardland Sirius is also an interesting example because it has this sort of set of weapons and items that are sort of essentially boundless. All of these examples of procedural content generation. So we're going into AI doing things related to designing and developing games. Procedural generation of game content, so with limited or no human intervention of game content, so not behavior on the game engine in all kinds of different games. And you may say that, okay, that's interesting, but this already happened, as I just said. Some kinds of PCG have been around since the early 80s. So what's the point in looking at this from the perspective of modern AI? Well, because I think that the prospects of procedural content generation, we're really just starting to explore it. There are lots of things that we would like to be able to do, but we can't. So can we, for example, drastically cut game development costs by creating game content automatically from designers' intentions? So basically, you're a content developer, or you're a game developer, and you don't want to do all the sort of grunt work. You don't want to sort of model every little part of this road or every character. You want to say like, hey, I want a forest over there. No, not that big. Smaller, but with taller trees, and also make it easy to hide in. And here should be a population in this village, and they should be different. Oh yeah, make them sort of, have some conflicts between each other. Make it so that there are some rich people, and you could specify things on a higher game on a higher level. This level over here, by the way, try to make it so that you can only finish it if you have bought one of the expansion packs for the game. Whoops. Well, I didn't want you to do that sort of thing, but yeah, you get the point that you could direct games at a much higher level and have the algorithms do all the groundwork for you. Can we come up with games that are endless? Not like in No Man's Sky, where you basically, there are like, I don't know how many billion stars, but you don't really care because they start looking a bit samey after a while. I mean, they're wildly different in colors and what kinds of creatures look there, but you sort of miss the overall structure. Can you come up with games that like, give you interesting stuff? So you play the next sort of Grand Theft Auto-like game, and you decide to go 5 hours in that direction, and there are things there. I mean, it just comes up with new cities for you, and in the cities would be new characters that have their own lives, and they have their stories. They have their own architectural style, and and there are things to do there. And maybe it's sort of geared towards you, so the game has figured out what you want and what you can do and what you're good at, and tries to sort of fix that up for you. I'm also of the opinion that humans are not very creative. We like to think we're creative, but if you tell a human to be creative, they will look at some example of what someone else has done and they do something like it. I think we could actually get past human creativity and sort of augment it a lot with sort of computer creativity that sort of gives us radical new ideas. And finally, from the standpoint of understanding game design, as a computer scientist, you learn that you don't really understand a process until you've written code that can implement that process. You don't understand sorting before you've written a sorting algorithm. I don't think you really understood game design until you have been able to sort of come up with algorithms that can design games. So I think there's a lot to do here. This is a really, really interesting way in which AI can possibly make games better. And there's lots of different ways in which you could do it. People have been throwing all kinds of fascinating methods onto procedural content generation. So these classical games like Rogue, for example, use all these ad hoc methods that basically mimic growing levels in various ways. There's things like Cellular Automata, noise, such as the ubiquitous Perley noise, and other kind of fractal algorithms are commonly used. Grammars are very often used for modeling vegetation. There's search-based methods using evolutionary computation, which we get to, those based on constraint solving. Recently, there's been some work on trying to use machine learning for this as well, which is a very interesting direction, but with a number of problems. So let's start from the top, and I'm actually not going to go through this list because, look, you want to get out here at some point, and you will fall asleep if I go through this list. So I'm actually only going to look at the first bullet point here. Search-based methods using artificial evolution. And I'm like, you're like, evolution? Yeah, so basically evolutionary algorithms are simply using, taking the idea of Darwinian evolution, of survival of the fittest, and using it in a computer algorithm. So you have a number of rabbits, and the rabbits that are good at, eating grass, avoiding the foxes, and attracting the attention of other rabbits of the other sex. However they do that, they get to have offspring, and those that don't, and the offspring is like them, and those that are not like that, they don't get to spread the genes. As a rabbit running from a fox, by the way, you don't actually need to be faster than the fox, you need to be faster than the other rabbit. So you have this sort of relative fitness criterion happening. This can be replicated. The basic ideas of these can be replicated in a computer. Extremely simple. We're talking about 10 lines of code. It's basically, you have a population of a number of individuals, and individuals here, you probably don't have rabbits, but these may be game characters, or game levels, or game rule sets. In each generation, you basically score them all according to some criteria, some fitness function you have. You sort them, so you have the most, the best ones first. You take the worst half and throw it away. You replace it with copies of the best ones, and you randomly change these copies a little bit. And this is almost criminally simple, and it works so well. In what we called search-based procedural content generation, you basically use evolutionary computation to search the design space for good artifacts, such as levels. And you need a way of representing the content so you can search it. You need a way of evaluating it, so what's good content. The big problem with this, of course, is that if you have a simulation of rabbit life, it's pretty simple to figure out what's a good rabbit. It needs to, not get eaten by the fox, it needs to eat grass, not get various diseases, etc. But what's a good game level? That's tough, right? You can evaluate what the good, if we're looking at levels, are in various different ways. You could try to come up with some way, like a neural net or something else, that looks at a game level and immediately gives some kind of value. You can sort of just count some things in the game level, and you want to maximize that. Or you can use an agent to play the level, or part of the level. Or you can ask humans. However, humans are expensive and slow, and avoid them whenever you can. I'm only talking about algorithms now, but in general. So say we wanted to use evolution to create levels for Super Mario Bros. How would we do this? How would we evaluate what's a good Super Mario Bros. Level? What can be algorithmically used to evaluate a good Super Mario Bros. Level? Yeah? Yes, you have to determine it's possible to beat it. And how do you do that?
Well, I guess,
If you know the physics, yeah. But is that enough, really? I mean, you can look at like the level that the gaps are wide enough and so on, but quite possibly that's not all you want from it. Maybe there are some other things that maybe there's an enemy standing right next to the level gap. Anyone else? How will we do this? How will you evaluate what's a good Super Mario Bros. Level? Yeah?
Maybe you can compute the difficulty of levels over from the start to the end, for example, based on the number of enemies and the number of jumps that are needed.
You could do that. Right, you could do that, but is that going to be a good? First of all, where are you going to get the numbers that say that what's a good difficulty? And also, this fitness function might come up with a level that basically is the same thing over and over and over. Maybe it finds a single part of the level that has the right difficulty, and it just keeps repeating it, which would be a boring level. Nintendo would spit at you, which is a bit of an honor. But anyway, yeah. What I'm giving you here is what is like almost what's called a wicked problem in design speech, because it's essentially unsolvable. But the nice thing is there's so many interesting but flawed solutions. So first of all, if we want to investigate if it is solvable at all, remember that agent I showed you before, like 45 minutes ago? You saw this agent playing Super Mario Bros. Yeah, obviously we'd use that. And we basically use that agent to try to play the level and see what happens. However, that agent is almost too good. So maybe there are levels which that agent could play, which a human just wouldn't want to play. So you might want a worse agent, right? Or maybe a more human-like agent. And then you don't want the level be the same thing over and over again. So you want it to you want different parts. You want to assure there are different parts, right? Anything else? Anything I'm forgetting? Yeah, I'm not going to torture you more because this really is a rabbit hole which you can go into and find more and more things you want to dig this into it. But one thing, I mean, this little thought exercise, if you're with me here, one thing is trying to come up with such an algorithm makes you think really deeply about the level design in a way that many other things don't. Which is even if you don't care about AI, doing this to understand game design is worth it. So a student of mine back in Malmö, which I was advising from afar most of the time, he basically tried to come up with a way of doing this. So first he came up with a representation where he looked at the original Super Mario Bros. Levels and figured out that almost all of it can be represented using 25 or so slices or columns. So basically, this is the level part here. You have level slice 1 and level slice 1 again, and here's level slice 2, level slice 1 again, and level slice 3, for example. So basically, if you slice it up like this, you see that there's there's only relatively small parts of slices or columns that are combined together. And then he found a number of high-level patterns. For example, the tree path, where you can go below, in the middle, or above, or a valley between two pipes, a horde of enemies in a valley, etc. And he decided to basically use this as a fitness function to use as a fitness that it should have as many different of these design patterns as possible. Using that, you can very quickly and easily come up with evolve levels that have a lot of local structure, which are pretty interesting to play. And then you can also vary which patterns you want over different parts of the level. You might say that, you know, I want a much higher pattern density in the second half of the level than the first, and so on. And you can come up with levels that have that are different in different parts. So at the level at the top here, basically starts out intense, it gets less intense, and then more intense towards the end, for example. I use this as a very simple example of level generation, because Super Mario Bros. Is sort of done, but it's sort of, Super Mario Bros. Has become sort of the Drosophila of procedural content generation, that everybody uses it all the time. Here is some very recent work from my lab under review, but this is Talakat, is a system by my student Ahmed Khalifa, for bullet hell games. Bullet hell games are games which are sort of two-dimensional shooters, characterized by having an extreme amount of different projectiles on screen at the same time, which often makes it sort of, you know, geometrically beautiful. So we came up with a language that describes each one of these bosses. They are basically all a sequence of these boss fights. It describes in terms of what different sort of spawners of bullets it has and so on. And then we're evolving this using something called map elites, which is an algorithm that makes sure you have a very high diversity among the different things. So let's see if this, I just got this video like yesterday. You play as a louse and you're invading a wig. So it's a lousy game. You see to the side here, you have description language that basically describes the boss, and you can sort of edit it automatically. But then you can also evolve it to get interesting paths. And when you evolve it, part of the fitness function is how the little louse spaceship. So here we have some generated levels. You can basically, it's simulated using an agent that we can vary its dexterity, so how much you sort of, you know, how much it can do sort of, how exactly it does these sort of small changes, but also strategies, so how far ahead it can plan. So you can get levels that need high dexterity but low strategy, or high strategy and low dexterity, etc. And you get very different patterns. This looks like there's a lot happening, but it's actually, as you can see, very easy. You just need to stand in the right place. But yeah, but some are much more complex. This is all game content. Let's look at, if we take a step back, if we don't have a game to generate content for, can we create a completely new game this way? So this is not my own research. This is research by Cameron Brown, who is the sort of guy that he was working as a software developer, and in his spare time he developed new sort of board games and wrote books about board games and so on. As particularly this kind of games, like recombination games, like Hex and Othello, 4 in a row, etc. Checkers, Go, so that have a very limited vocabulary of different pieces and so on. And then he decided to do a PhD in computer science, which he did on evenings and weekends. He is that kind of person. And he came up with this system, which is called Ludi. So it starts with a population of, I think, 80 or so well-known games. And then you select parents for these games. These are represented in this simple game description language, which looks a little bit like Lisp. You cross over the parents, so basically these games have sex with each other, they have kids, these kids are mutated, slight changes applied to them. You check the rules. So do the rules contain such things as like, both players have moves to take, it is possible to win the game and so on. If so, you go on, otherwise you throw it away. Then you give it a name. And then you try playing it. If you never get to the end, if it's too slow, you throw it away. Otherwise, you sort of optimize a policy. So you optimize a neural network to be used with this tree search algorithm to play the game. And if you get a draw all the time, then you throw it away. Otherwise, you check if it's inbred, then you throw it away. And then finally, if it passes all these tests, you give it a fitness. And the fitness calculation is pretty complex, but a lot of his game design knowledge went into this, because this is a person who had thought very deeply about the design of these kind of games. One of the important fitness measures, or several of them, have to do with how late in the game you can tell who's going to win, because you don't want a monopoly situation where you have like a feedback loop. So if someone starts winning, that person is going to win, etc. So you want something which you can decide pretty late. And then you put it back in the population. As you can tell, this is a very complex process, and his runs took like a week each. One of the results is this game called Diablo, which you can buy in a box set. It consistently ranks in the top 100 on Board Game Geek. It is a game about getting 4 in a row without getting 3 in a row first. It's very clever, very good. As you can see, you probably can't read it, but under Diablo it says by Cameron Brown and Ludi. That's actually not true. The game was designed by Ludi, the system. Cameron Brown just designed Ludi. So, and the game is sold, and Cameron is getting all the money, but his system is not getting any of the money. I don't know. What's the... But yeah, I think this is brilliant science. It's a good example of that these kind of systems actually can design complete games. Here's another interesting way in which this can intersect with the real world. So we use algorithms to design game content. We really showed you these sort of bullet hell patterns, the Mario levels, and now game rules. But the world is full of content, and so much of it is available for free online. There's all of Wikipedia, OpenStreetMaps, and lots of sort of public databases of lots of different information. And can we create game content automatically from open data? So we've done a number of different what we call data games. So I've been coming up with games that build Monopoly boards out of open data, games where you play on a bar chart, and you change what you visualize, or that create simple card games based on open data. But then we have this set of games that we call data adventures that mainly one of my PhD students, Gabriela Barros, has been working on. And the latest in this iteration is Data Agent. Data is Detective Agency of Time Anomalies. So it's sort of a Star Trek-like scenario where you need to go back in time to solve, someone has invaded the timeline and killed a famous person. And you need to, so someone has killed Albert Einstein here. And you need to basically move around and figure out who did it by asking people questions. So you travel around to different places, and you ask people questions about their relationships and who they are and where they live and so on. And all of these people, everything in here is taken from Wikipedia and from OpenStreetMaps. So it's sort of, every time you type in a different name into this game, you create a completely new game out of crawling Wikipedia, using evolutionary computation to find interesting sets of complementary suspects. And you can read a lot about places you go to. You can go to the German Empire, United Kingdom, and Bern in Switzerland, etc. Kurt Mendelssohn, and he wants you to go to speak to some Fritz guy, for example. And one of these people is lying, and he's the murderer, or he or she or it or whatever it is. And then you need to find out by sort of essentially cross-examining everybody. This is it's a relatively hard game, but we recently sort of And it has like a very annoying capacity of coming up with extremely inappropriate things sometimes. With like you visit a police station and there's a picture in the background of police beating up protesters somewhere, for example. And at some point we had Adolf Hitler appeared and he pointed to someone as a suspect because he was a Jew. And yeah, so you know, it's like this comes out of the data. Also, did you know that Wikipedia has a lot of inaccuracies in it? It has a lot of like, it has a lot of things like cities that appear to be in the middle of the ocean if you look at coordinates and so on. Right. Another way in which these algorithms can interfere with the real world is that maybe, I mean, sure, not everything can be automatically generated, but could you actually collaborate with these algorithms in an interesting way? Because humans, after all, sometimes they are creative in some ways. So how can we work together best? So this is the domain of what we call mixed initiative, or what many people call mixed initiative interactions, where you have systems that use AI to create things, but that you also collaborate with them. So one example is the Ropossum system, which is a system for generating level for the physics-based puzzle Cut the Rope. It uses evolutionary computation again to create new puzzles, and it uses a form of tree search to testing if you can solve the puzzle, and then you can at any point as a designer change the level in any kind of ways and request feedback or testing or regeneration of any part of the level. How many of you have played Cut the Rope? Well, about half of you. It's a good game. This is basically you have a piece of candy here, and you need to basically move it around in some way and then cut ropes and push it around with bubbles and stuff like this to feed the candy to the little monster. It's very cute. So here's the system. Does this video start? Yeah. So it can automatically generate any number of levels. You just press a button and it uses evolutionary computation to create a new level. It's fast and reliable, and the levels are all playable, but they don't look that impressive. So let's start by designing a new level on our own. So this is an interface where, just as you would expect, you can essentially drag and drop. You can place items around. These are little bumpers. They work like flipper bumpers. When the candy touches them, it bounces away. And here's a balloon, which you can use to blow it. Here's a bubble that the candy can get caught in. And here's a rocket. You check, is this playable? By pressing a button, and it uses, you see at the top here, it will give you all the different steps you need to take to actually play the level. So you blow this, and it moves into the rocket, and you jump off the rocket into the mouth of the little monster. Nice. And what we use for this is a depth-first search augmented with Prolog to reason about what are reasonable actions to take. Then you can say that I want to keep some parts of this level, but I want you to regenerate some other parts of this level. So let's say that these things stay here, and now create the rest of the level. Okay, nice. How does this level work? This is very simple. You just cut all the 4 ropes in a sequence. That's not very interesting. So let's do it again. Let's keep some aspects and regenerate the rest. Okay, so how does this work? It's actually deceptively simple because you need to swing the candy into the rocket, and then the rocket shoots into the bumper, and then the candy bumps off, which is probably not something you would think of, because you wouldn't think of that it would bump off there because it's only on the rocket. So essentially, the level editor suggests a solution to you that you might not have thought of yourself. It essentially helps you be creative. Another system that we built is built for generating, for helping you create strategy game levels. This happens at a slightly higher level. So basically, we have these abstractions of levels that can turn into strategy game levels, for example, for StarCraft. We have things such as bases, resources, impassable areas, and so on. And this system constantly gives you suggestions. It also gives you lots of metrics, like, hey, what's the balance of this map? How much free space do you have, and so on. But it also gives you suggestions on variations you might want to take. It takes the levels you have and sees if you can modify them a bit to make them more or less balanced, or so on. So, and as you see here, this very simple block-based interface here can then be extracted into more detailed levels. Let me see if this moves. Yeah, so you start by placing bases here, and then you add resources. As you can see to the left, you have these suggestions happening. So as you're editing, it's constantly analyzing what you're doing and trying to add suggestions how to sort of vary the design a bit. These impassable tiles are immediately mirrored in the suggestions. You can look at which safe resources there are, and there are no safe resources. So you add some safe resources, which are those that you can easily get to without being contested in any way. The passable space around each space is similar. It's good, so we have, it's pretty fair in that sense, the map. What unused space you have. There's level segmentation, so a number of different metrics. You can select to use one of these suggestions. The editor will then learn what your preferences seem to be and modify the way it makes suggestions in the future based on what kind of things you seem to prefer. So it's trying to adapt, it's trying to learn your style of designing at the same time. Right. And then in the end, you can basically export this in a number of different formats. And because it is so abstract, the plan is you should actually be able to export it as, for example, dungeons and so on as well. The idea is that certain aspects of level design are so generic that they should be sort of transferred between different game types. Moving on, yet another thing people do is that they teach each other to play games. And this is some ongoing work that we are just about to submit about generating tutorials. So we're using this general video game AI framework. You remember the Zelda game, for example? And trying to come up with a way of automatically generating tutorials for it. So it is based on the idea that we can both understand the rules, so we can symbolically reason about the rules, and we have agents that can play the game proficiently. Then we can look into the rules and see which sort of things are necessary on the path from starting the game to winning the path, where you need to kill enemies, you need to get health packs, for example. And it tells you these things, and then it finds aspects of when the agent does it and actually shows it to you. So it gives you visual examples of this being done. So this is an example of the Zelda tutorial. It shows you how to get points and how to lose and how to win. And how to win actually gives you all the things, like if the goal door and you avatar with a key collides, then the goal will be open. And so it shows you, in each case, it shows how to get the key and then how to go to the door. And it shows you how to lose, how to not get, basically move into an enemy and so on. So it's it generates both textual and visual descriptions of this. Right. So I've taken you on this tour, starting from coming up with ways of using games to test AI, and then moving into different other things you can use with AI for in games rather than playing them. Looking at how you can generate things in games and how you can generate things together with humans and based on data, or how you can teach games and so on. Let's actually go all the way back to the start again and try to tie things together. We talked quite a bit about general intelligence, and I even showed you an equation. I'm sorry about that. We talked about general intelligence. I'm not sure there is such a thing as general intelligence. I think sort of the jury is still out on this. So we've been programmed for decades by, our friends, family, other parts of society, school, to do a couple of a small range of very well-defined tasks, using the curricula developed by society, maybe whether or not it's called curricula. Most of us are very special purpose. I can't do most of the things that are necessary to make society function. I mean, most tasks that are done by humans in the world, I'm completely useless. And then most tasks that are done by any kind of creature in the world, I'm even more useless. And it's not just me. I mean, you too, right? It would take you, any one of us could probably become a decent butcher or lawyer or something, but it would take years. I don't know if it's harder to become a butcher or a lawyer, but it's probably similar. So I don't know if there is such a thing as general intelligence in that sense, because we basically need to reprogram ourselves. And we feel very intelligent because that's because we built this really, really, really complex society to make everything easy for us. Everything is sort of adapted to us. So there is this idea in computer science that because of Turing completeness, any process can emulate any other process. But that's sort of irrelevant because you need, as anyone who's actually ever written software knows, it's hard. Just because a computer can emulate another one, it doesn't mean that it will actually do it, that we know how to do that particular task. There's a theorem in machine learning called the no-free lunch theorem, which basically says that over all possible, and it's a similar one for learning, over all possible problems in a bounded time, in a specific bounded time, all possible algorithms are equally good or bad. It's called the no-free lunch theorem, and what it basically says, it seems like a very pessimistic thing. That's like, why? Progress is impossible. But actually, most problems that we face, almost all problems, are from a very, very more limited distribution of problems. So basically, we live in a society which serves us a very much more limited set of problems. We don't have to solve any kind of problems like, certainly not the same kind of problems that a fish would. So in a sense, making progress in AI is important, or is possible, because we can get better at a limited set of problems. And I think that game playing is, because it is tailored to be interesting for our brains, and we are making them as a culture and as a human species to be interesting for us, they are therefore the most relevant AI benchmarks. So essentially, it's impossible. General intelligence probably doesn't exist, so AI is essentially impossible. But we can make a lot of progress on the type of AI that matters for us. So we can do our best to come up with machines that solve as many problems as possible at the same time. And the best way to do this is to teach AI to play and design games. And as we've seen, many of these methods can also be used to give us better games, which is, even if you don't care about general intelligence, is a good enough reason. We have a textbook in procedural content generation out since 2 years ago. We also, since very recently, have a big new textbook on artificial intelligence in games, which contains many of the arguments and material you find in here and much more in depth. We're also running a summer school this summer on AI for games, which unfortunately is terribly located in the island of Crete in Greece, so in May, but still, you can go there. And that's it for me. So thank you.
Thank you, Julian, for a great lecture on artificial intelligence and games. Would audience have any questions for Julian to kind of address? There's quite a lot of already addressed here. Well, while you think about your questions, I have couple of questions.
Oh, wow.
So first of all, like I'm studying game developers, so
Yeah.
I'm just wondering what is the future of game makers. So who is actually, because we still probably will need you humans,
Oh, yeah.
but who is the future game maker?
So, I mean, I usually have different answers to this, depending on if I'm talking to computer scientists or to designers. Because the designers tend to be a little bit defensive. Oh no, you're taking your jobs away. And I'm not saying that. I mean, you're not coal miners. I mean, coal miners actually are losing their jobs, but game designers are not. I'm thinking that what we're doing is trying to move game designers sort of up the value chain. We don't want you to be doing all the sort of grunt work. In a way, it's a similar thing to what happened in the advertising industry with the advent of Photoshop. Suddenly, you had a whole category of people who were like only doing, I don't know what they're called in English, but basically the people who were only sort of producing the actual picture. And there were so many fewer of them needed because the IDs people could then actually suddenly go in and make the pictures themselves, including all the details. And the people who were doing the craft work, they either had to move up the chain and becomes more IDs people or move somewhere else, which is not that uncommon that what goes on in every other profession in the world. So basically game designers, I'd like to see these tools basically make game designers more productive in a way. So who are the game designers? Well, people with IDs.
So idea peoples are
IDs.
going to be useful.
I'm saying this, but I was also head of the Games Masters program at the University of Copenhagen for 2 years, and one of our big decisions there was to sort of make sure that we would not admit any pure IDs people anymore because they were useless. IDs people are useful, but not pure IDs people. We were looking specifically for people who knew some kind of crafts, like making either coding or making music or making writing or something. What I'm thinking is like operating. So crafts will still be necessary, but operating the algorithm, so to speak, will probably become a more and more important craft. Understanding AI, not at the level of writing the code, but understanding what can be done, what can search do, what can learning do, these things will almost certainly be much more important.
So will it be so that the designer creates their own algorithms so that they can kind of direct the game as you were visioning?
To some extent, yeah. Or like modifying existing things. I mean, if you, for example, use deep learning for some of what you do, there are these very, very useful scripting languages for deep learning algorithms where you can express these complex things you have in like 10 or 20 lines of script code, and you can download someone else's code. If you know a little bit what you're doing, change it around a little bit to fit your own purposes. And I think this will be a game design and development craft which will be every bit as important as painting pixels, or probably more important.
Yeah. Other questions from the audience? There is one. Can you wait for the box?
A box?
Hi, thanks for the great talk.
Thank you.
So can you comment, kind of related to your question, is there such a thing as general intelligence, or are we as humans intelligent? What is the state of the art of transfer learning in games? Because I see many AI researchers saying that we need to get to human level transfer learning, but humans suck at that really.
Yeah.
So
So the state of the art of transfer learning in games is probably the paper from a few weeks ago called Impala from the DeepMind team, where they managed to teach the same neural network to play 57 different Atari games with some kind of decent performance. However, they did this by an extreme amount of computation. We're talking about many, many tens of millions of game steps played. I don't have the numbers in my head, but it was something like, this is ridiculous. And for comparison, the famous Nature paper from 2 years ago, where they taught a number of neural networks to play games, you had basically each neural network played for the equivalent of 36 days of game time, the same game. Now, if you would have played one of these Atari games for 36 days straight, 24 hours a day, you would probably be very good at it, or insane, or both. These algorithms are still extremely inefficient because this transfer learning algorithm is much more inefficient than that. What we need to take into account here is that we as humans coming in to play a new Atari game, we are drawing on a lot of knowledge which we gathered throughout our whole life. And that's really the kind of transfer learning we want, and we're nowhere near that.
Yeah, and those Atari games, they're kind of toy problems for transfer learning. So in many real-life problems, humans have difficulty transferring skills. So it's really hard to switch professions, for example.
Yes, it is. And also, I mean, that particular paper that I mentioned, the Impala paper.
So how do you spell it?
IMPALA.
Okay.
Like the animal, or like the old Chevrolet model that you hear about in the hip-hop lyrics all the time, or I do. But anyway, it's I am not sure that it doesn't simply learn a number of different policies and learn to switch between them. I haven't seen proof of that. But yes, sort of transfer learning to sort of do many different tasks at the same time, there's a lot to do, let's say.
Other questions?
Yeah.
There? Please take the
box.
The box.
Okay, hi. First, thank you for the amazing presentation.
Thank you.
I have a very practical question. So for a person who is interested in artificial intelligence and games and is currently studying artificial intelligence and also an enthusiast for games, what are the places in the world where one would continue with the education and research in these fields?
Well,
in your opinion?
Start by going to the summer school over here. And you can also read these books over here. But yeah, it depends.
Just some recommendations. So.
Yeah, no. So in the US, it's either us at New York University or Georgia Tech or University of California, Santa Cruz that have like significant groups doing this kind of research. To Drexel University to some extent as well. But they all have different profiles. So for example, the Santa Cruz people are more focused on the narrative parts and on symbolic AI, but they do a lot of important stuff. In Europe, it tends to be scattered all over. The closest, the closest thing I can think of, well, of course, apart from Pertu here, who's 2 meters from you. But there's IT University Copenhagen, which have a few people working on that, where I used to go before. But otherwise, it's very scattered around with like people all over. Oh, Queen Mary University of London, Simon Lucas's group, is pretty big as well. Yes, Pertu?
So in Europe, I think the UK IGI funding. So
yes, yeah. So the IGI, the Intelligent Games and Games Intelligence PhD School, which includes Goldsmiths University and Queen Mary University in London, University of York, and Falmouth University. And there's a bunch of people around there. And I think they're still accepting PhD students. So that's worth looking into, yeah.
Julian, you're saying that games is the best thing to study with the artificial intelligence in kind of for the both directions to also advance the AI studies. But would it be still kind of beneficial for the students to find a general AI study group as well and not just only games? Or are you biased to answer to this?
I'm extremely biased.
Yeah.
You know, I don't, but there are lots of other interesting areas. What I would say is that, I mean, if you're interested in AI in general, find a domain that motivates you. Games motivate me. I mean, there are other things that are interesting as well, but you know, they may be less interesting. But don't get stuck in a particular method. Right now, there's a lot of talk about deep learning, and people want to use deep learning for everything. And even some people in games companies are it's almost like this made me think of this particular slide I had over here, all the way at the end. Again, yeah, exactly. This is sort of the mood in in some of industry and a lot of academia these days, and it's sort of ridiculous because really it's like just one of very many methods that all have their different advantages and disadvantages. So whatever you do when studying AI, don't get stuck on a particular family of methods. Do dig into deep learning. It's great. It has fantastic results for a number of things, but learn about other machine learning methods such as, you know, random forest and so on. Learn about things that are not machine learning. So learn search algorithms and symbolic reasoning and so on.
Are those your keywords that makes you excited, or is there something more kind of very new that you are just recently very excited in the field of artificial intelligence?
No, I mean, saying this, I am actually quite excited about a bunch of different developments in deep learning recently. But I try to temper it a bit because I know that we're all sort of, you know, on the same bandwagon. And as any bandwagon, you're on a bandwagon and eventually it will sort of go through the ice and sink. So I don't know where we're going with these metaphors, but
maybe you can still save yourself before it actually sinks. So
yes,
it's not that
exactly.
bad to
So
go with the bandwagon.
yeah, maybe sort of have one foot on it and sort of
Yeah.
wear a safety vest.
Yes. There is a question from Solid. Can you wait for the cube to come to you? Or maybe you can throw it. That's the point of
the weighted
well, we are
companion?
not throwing it, apparently.
Is it
Go
a
ahead.
weighted companion?
Apologize in advance. I want to ask some philosophical question here. I
Yeah.
remember in the early slide you mentioned that you started with philosophy, and I remember almost in the very end slide you mentioned that this whole process is about AI and using AI for making a better game.
Mm-hmm.
So, as a person who's studying game cultural studies, the question would be, what do you mean by better game? So let's narrow it down to your fields, like in your research or your interests. What's the core value that you're aiming for? And how do you define better game in your research?
Yeah. I don't think there is a straight answer to it. I mean, I could be, if I was a really annoying person, which I sometimes am, I would say, well, if it sells more, it's better, because that's how a lot of the game industry reasons, because that's basically, obviously people wanted it. I could also look at it from the cognitive point of view, and if it challenges our minds in an interesting and engaging way that other games have not done before, that makes the games better. I mean, I also tend to look at it from the sort of, you know, is this a new form of gameplay that we haven't seen before? So basically, why do we create new games at all to start with? I mean, there are lots of games. There are clearly more games around than any of us could play. And, you know, there are clearly more novels written than any of us could read. But we're all like searching for the new, right? We're searching for new and interesting that says something new about big words, but you know, the human condition. And obviously games don't say things about the human condition in the same way that novels do, but they still do say something about the fact that we like performing an activity in a simulated world says something about us. And that's yet another important way in which a game is good. Like you can make an engaging activity of something we didn't think we could make an engaging, playful activity out of, I think.
Maybe following up to that is that would we be able to, with the help of AI, designing our games, would we be able to kind of create games that would explore things that we haven't explored yet in games? Because that's one of the things that we are fascinated by digital games, that they provide us the adventures that we wouldn't have otherwise. So
yeah.
Do you see that as a possibility, like the further possibility?
Yeah, I think so. I mean, one idea behind the data games, I'll show you this data agent game, one idea behind this is that you could basically create something hyper-local and hyper-personal, and basically look at like, can I create like an RPG or an FPS or something that takes place on my street, you know, based on publicly available map data and data about who lives here and everything like this, and create something that's just like here and now, so it's more meaningful for me. Or T.L. Taylor, I saw that she's the final speaker this semester. So T.L. Taylor is now at MIT. She was my colleague at University of Copenhagen in our super interdisciplinary games group. So she's an ethnographer, and we both do games. Otherwise, we're disciplinary so far apart. And I had my office right next to her, like for a few years, and it was great. We had all these super productive disagreements. One of my favorite people to disagree with. I really like her and I really sort of appreciate her work. And we did and do have very different opinions about things. And one thing she was talking about how every game has a social aspect. And I said, no, not for me. I like to basically draw the curtains, turn down the lights, and play the game without talking to anyone. You know, I'm an asocial gamer. Go away. And then she's like, no, but you talk about the game, and there's a culture around it, and people write sheet guides on the internet and so on. And I'm like, grumblingly had to admit that she was right, that it was a social activity, and I really, really disliked it, and I still do. It's Finland, so I feel free to say this, but you know, can other people please stay out of my games? So another vision I've had for a while is basically, can we use these methods to create games that are completely personal, that are only for you, only you can play. You can't talk about it with anyone else because no one else has the same game and can play the same game, which would be beautiful for me.
So should we rewrite Matrix and just make it look that we would be more happy with the games that we play would be about us?
Yeah.
Or the life, the game.
Yeah. Why not? Why not? It's like,
or at least for certain people.
Solipsistic games.
Yes.
Why not? You know,
Exactly.
I mean, people talk about how we're isolated, but these days modern technologies are also social. It's like you have all the people around you all the time. How can we get rid of it? Yeah.
Other questions? More philosophical or non-philosophical questions? Yeah. Can you throw that mic to the next person? Oops, almost.
10 points.
Now it's in the no man's land.
No man's mic.
Thanks. Well, like listening to this, like about things about AIs playing games, and on the other hand, creating content for games. Well, this sounds like a situation ripe for a generative adversarial network where you have one AI playing the game and another creating content for it. Do you know of any interesting like applications where this has been done? Say, for example, the Mario level generation would sound like something that could benefit from this.
I could either go off on a rant about like deep learning centric stuff, or I could go into the historic rant about how generative adversarial nets are actually just a reinvention of the same principles as competitive co-evolution in evolutionary computation, which is really interesting, but they actually work better. But instead, there is a paper submitted to Gecko by a group of people, including Sebastian Risi at the University of Copenhagen, Adam Smith at UC Santa Cruz, and a couple of others, that does generative adversarial nets for Super Mario Bros. Levels with pretty decent examples. I don't know if it's going to get accepted or not, but you'll see it in print sometime soon. We also have a survey paper called Procedural Content Generation via Machine Learning, PCGML. You can type PCGML into Google, which shows an acronym that no one else has, which is very useful. It's unpronounceable, but it's like, that will give you a couple of examples of like, of using machine learning to create game levels. In general, my general comment on this is it is possible. You lack what you need to mix it up with something else, because the machine learning can't really. You need some kind of search procedure or simulation procedure to check for playability in most cases. But the real problem with content generation for machine learning, or like machine learning for procedural content generation, is where do you get the data? And this is the big problem. So we've been thinking about this. There's been a number of different attempts to do this with Mario levels and with StarCraft maps and other things. But you know, there's like 25 levels you can use in the original Super Mario Bros. There's like 100 Blizzard-approved StarCraft maps or something. So where do you get enough good data to train on? This is the problem. So modern deep learning can do amazing wonders if you have the computation power and the data. And in this case, you very often don't. So you need some kind of transfer learning. So you need to train, if you could train on all kinds of different platform games and then produce only Mario levels, that would be amazing. That's a big, outstanding research challenge that I don't know how to do, but I'd love to have someone working on that. But yeah, it's promising, but we really have a data shortage at the moment.
More questions? Well, I have a final question about iteration in game development. That's one of the most expensive parts of it. So I know that to some extent this kind of approaches are already used, but do you see that as one of the kind of most kind of closest to us as an application for?
Yeah, so the most low-hanging fruit, to the part where modern AI methods are actually used in game development, not design these days, is like data analysis, obviously, where you basically look at all the sort of logs you have of like modern games, and you basically try to predict what players will do and identifying player types and so on. But the other low-hanging fruit that many game studios have really understood that it is happening and is game testing, automating game testing or pseudo-automating game testing. Whenever you make a change, you compile your game and then you have agents of different skill levels and different sort of things different play styles that play through it and give you a report on the content and figure out if you broke something or if something is reasonably easy or hard or something. This is definitely going to change game development. And it's definitely going to change development by removing the most boring part, which is playing the games. This didn't come out right, but
in the development,
yes,
playing your own games.
Yes, right, exactly, because you get tired from it.
Okay,
right.
Thank you, Julian, for your lecture today, and thank you for the audience for having questions and coming here, as well as online viewers of the lecture. So Games Now is a lecture series that is open for everyone, so make sure that you follow and subscribe our social media channels, YouTube and Facebook, and also spread the message to your friends. They might be interested in the topics. I am Anna-Kaisa, and please come again next time. Join us here physically on the location at Aalto University or join us online. Thank you.
Thank you.